our next speaker, we call David Blair.
Hi everybody. Thanks to the chairman for lending me his computer. My computer failed on this projector. And thanks very much to George for setting the scene for why what I'm talking about is even more important. I'm talking on behalf of a whole lot of people who've been working on the idea of future detectors of gravitational waves, and in particular I want to sort of acknowledge this group and this paper, which is actually coming out in final version on the 1st of March, which is called Host Galaxy Identification for Binary Black Hole Mergers with Long Baseline Gravitational Wave Detectors. But it's focusing on some detectors in the Asian region. The bottom line of the paper is that a significant number of host galaxies can be identified by gravitational waves alone if you have an improved array, and that at larger distances you can do statistical associations, and I'll mention it again later because it also helps, I think, with what we've just heard about. But I just wanted to respond to Svi Piran's comment in the first the introductory lecture for the conference yesterday morning, where he talked about how transient astronomy was a real sort of contradicted sort of dogmas of Western thought. But I thought that, especially here, it was important to emphasize that it completely doesn't contradict the dogmas of Eastern thought. And this is a quote supposedly from Buddha: impermanents are all component things. They arise and cease, and that is their nature. They come into being and pass away. And all conditioned existence, without exception, is transient, evanescent, and inconstant. So Asia is the place for transient astronomy because Asian philosophy already thinks that way. And I think you can also see some practical aspects of it, which was the first seismometer was constructed in China in 132 AD. And today we listen to the whole of planet Earth with seismometers. We can hear our planet, hear every major change happening to the planet. And supernova 1006 and 1054, the story about supernova 1006 is absolutely fabulous story of science and politics, but haven't got time to go into it. But those were recorded by China and Japan, and there was always this interest in transient astronomy here. So anyway, that's my little bit of philosophy. But the discovery so far, we've heard a lot about it from Ray Weiss and other people. It's maybe George's taking George's talk into account. Perhaps it's still a surprisingly large population, but we don't really know what the population is of binary black hole coalescences, but it's of the order of 100, according to the current data, hundreds per cubic, there's a mistake there, 100 per cubic gigaparsec per year, not megaparsec, gigaparsec. And binary neutron star coalescences look as if they've got a density about 5 times larger than that. The numbers that we have now allow us to make predictions for the future, and we can anticipate mapping the whole universe in gravitational waves, just like today we can map the Earth in earthquakes with seismometers. So the question is, how would a pair of next generation gravity wave detectors in the Asian region contribute to world gravitational wave astronomy? And that's the particular question we set out to ask. we're talking and in my talk I'll mention a little bit about the fundamental physics of gravity wave detectors. Oh, it's going forwards all by itself. About the requirements for next generation detectors, a little bit about learning from LIGO, near-term possibilities and longer-term possibilities, but I also want to just refer to Julie's talk later today, which is going to be talking much more about the details of this. But here's what happened over the last few years. We saw a threefold sensitivity increase from the initial LIGO detector, which is that green curve, to the curve where we detected the first gravitational waves. Just a threefold improvement, and that threefold improvement took us from not hearing the universe at all to suddenly being able to hear some things clearly. So small change. One important thing is this is amplitude that we always use in gravitational waves, and energy goes as the square of the amplitude. So, but still, that factor of 3 made a big difference. Advanced LIGO has got, as Ray Weiss emphasized yesterday, has got a good way to go yet, and so we'll have a whole lot more science coming out of that. So, just a little repeat introduction to the gravitational wave detectors. Here's the Virgo detector in Cascina in Italy. It's a huge interferometer, here somewhat distorted and making the Earth look round, but which it is anyhow, but not quite that radius of curvature. You can see the huge long beam pipes and the big central installation. And what's in there, I think you all know roughly what's in there, but it's an interferometer. And it started with the idea of a Michelson interferometer, but the Michelson interferometer then has a pair of mirrors added to create optical cavities that resonate the light between the arms. And then another mirror is added, which Ray Weiss talked about yesterday, the power recycling mirror, which takes the laser light back in and resonates the whole detector to build the power up. And in the end, you can, the plan is to get the light intensity up to 800 kilowatts. This is a scary amount of power inside the detector. And finally, another resonance, which is very important, is the signal recycling mirror, which resonates the light and actually can change the sensitivity in many ways. I'm not going into any of those details. Julie's going to talk about some of that this afternoon because there are many exciting possibilities associated with that. With this technology, we've created the most sensitive instruments ever created. They can measure displacement scales of attometers. They can measure at energy scales of 10 to the minus 30 joules. And we're making quantum mechanical measurements of the relative position of 40 kilogram mirrors. It's amazing that these macroscopic things are still quantum mechanical. Ray talked about the noise in these detectors, and I want to just give a very simple thing because this lets me explain the motivation for the next detectors. You saw the sensitivity curve, which I've just turned for cartoon version into a sort of curve like that. And this is a frequency scale along here. At low frequencies, there's seismic noise. And seismic noise does two things. As Ray said, it makes the ground is vibrating with an amplitude of about 10 to the minus 6 meters, and you have to reduce that to be able to get sensitivity. But that motion of the ground also transfers noise into the detector at higher frequencies. So it doesn't only have a problem here, at the low frequencies, it also introduces noise up here. So we thought you just had to make your frequency band of interest the one that you work, that you get the vibrations low enough, but you actually have to get below that. You have to make it work much better to make it work properly at high frequencies. So that's one of the technical noise sources that's very important to solve. Then there are these two blue ones, which are both quantum noise. And one is the statistical force variations acting on the mirrors because of the fluctuations in the number of photons. So the radiation pressure is exerting a variable force on the mirrors, and that acts at low frequencies. But here, the photons are just coming at random, and that we call shot noise causes the sensitivity to get worse and worse at higher and higher frequencies. And that's a very important issue. But now in the middle, we have this technical noise source, which is the thermal vibration of the atoms in the whole system. I won't go into the details of it, but what's important is how you can reduce these effects. Seismic noise, you can measure seismic vibrations down to 10 to the minus 12 meters, and the typical vibrations are 10 to the minus 6. Because you can measure it, you can take it away by feedback. So this can be reduced, and you just have to do the work to do it. It needs very good engineering, but it can be done. The two blue ones, and Julie will talk about this in more detail, I suspect, this afternoon, can be reduced by quantum squeezing, which is this method of changing the statistical uncertainties in the two quadratures of the light. I can't go into the detail, but this has been demonstrated, and particularly in this band, we know it's a method that will work, but it has to be improved. This one, you can try to get better materials, but we've been trying to do that for years and years and years and been making very slow progress. But there is one way you can reduce this, and that's by making the arms longer. You don't actually reduce the noise, but what you do is you reduce the relative contribution to the arm length. So this is the main driver for making detectors much longer. And so from all of that physics comes the ideas of how you might want to make better detectors. And long ago in Europe, they proposed the Einstein telescope, which is a 10-kilometer triangle. So from 4 kilometers, you take it to 10 kilometers. Cosmic Explorer has been proposed mainly out of MIT, and that's 40 kilometers. And the one that I'm really talking about here is this Asia-Australia Gravitational Observatory idea, which is just taking a step over a factor of 2. And what we wanted to analyze is what you could do by taking what seemed like a fairly safe step, a factor of 2 improvement, making it 8 kilometers. No, the interferometer won't stretch that far. There's clear consensus that you've got to make the detectors longer to dilute the local noise sources. When you do the sums, you find that this would give you something like 4 times improvement in the sensitivity if you just are quite cautious about most other things. And the question was what science that would offer. So this was explored actually 2 years ago or 2.5 years ago in Beijing, and we presented a sensitivity curve for a detector like this, where what we have here as the top one is the advanced LIGO sensitivity curve, and here is the sensitivity curve for an 8-kilometer detector where you made the masses bigger from 40 kilos to 80 kilos, suspend them on pendulums that were twice as long, nothing too hard, just fairly straightforward steps of a factor of 2, and squeeze light, squeezing by 8 dB. I think the best squeezing observed in interferometers up to now is about 4 dB, so you have to do better, but not lots better. And so the rest of my talk is about what the science of what this that this would do. And this does 2 things. One thing, it puts more detectors in the world array, and the other is it adds more sensitivity. But it just adds to what's already there, or what's coming. So the idea was this, that you created a pair of detectors And what that immediately does is create extra baselines between detectors. It turns out that these two detectors create 9 new, you can just count and see, 9 new long baselines and 2 new short baselines. Short baselines are useful if you want to see the stochastic gravitational waves which come from where you're trying to see the common noise present in pairs of detectors, and you'd like them to be fairly close together for that. The best pair for that at the moment are the 2 LIGO detectors, and here you would be able to increase that. And now I just want to first of all remind you about this idea of standard sirens, that gravitational waves tell us the distance. This animation is just showing how it all works. You scale the frequency and scale the amplitude and model the noise and finally come up with the best fit. You probably didn't have time to read the little animation thing which was showing what the distance was and what the mass was. Of course, George has told us that this is all wrong because possibly all wrong because of gravitational lensing. But in the absence of gravitational lensing, this tells us something about, well, the luminosity distance. Of course, that method has been demonstrated from GW 170817, as we've heard before, but I'm just emphasizing the fact that this has allowed us to tell the distance. But the important question is, if there was no afterglow, could we identify the host galaxy? And that's, of course, what we would like to do for these black holes as well, because if with these black holes we could say what galaxy it came from, we could find out if George is telling us the truth or not. We can find out if there was a galaxy at 400 megaparsecs that was the source of GW 150914, for example. So we've just seen the standard Siren concept proved by GW 170817 because we saw that it was a distance of 40 megaparsecs. It agreed, and we got a Hubble constant measurement so that it all appears to work in that case. And so because of this standard Siren property, what we're able to do is create each binary coalescence event allows us to locate it in 3 dimensions in the universe. We get direction and we get distance. And so there is some error ellipse for every error volume, an ellipsoid, that determines the spacing. We saw with 170817 how the error ellipse shrunk when we went from the LIGO, just 2 LIGOs, adding the Virgo data, the non-detection by Virgo, and the error ellipse dropped from some 100 odd square degrees down to about 30 square degrees. That's shown on that slide there. We saw that already yesterday. So the first person to think carefully about angular resolution with gravity wave detectors was Kip Thorne, who presented a simple formula which says measure the time delay between different stations and use some simple algebra to determine the time. Yanbei Chen and Linqing Wen published a formula which is basically the same thing, and it's basically something we all know. It's the Rayleigh criterion, but applied to gravitational wave detectors, that shows that the angular resolution can be improved by it improves inversely as a signal to noise ratio, and that which makes sense. If you have a bright source, you can determine the location more precisely, and this enables you to go out and analyze any array and determine what its angular resolution will be. If you add, as we've considered, 2 detectors to this world array, we've suddenly gone to 11 extra baselines, lots of extra triangles. Yeah, it's clear that you can improve things a lot. So how good do you want to be? This thing automatically jumped forwards again, but hopefully it's going to stay there for a moment. We want to know what's the typical error volume for galaxies at the distance of the bright gravity wave sources we've already seen. And what you can see is that there's, if you can get to angular resolution of 0.1 square degrees, you can pretty well identify a host galaxies at a redshift of somewhat around 0.1. So we did an analysis, and that's in the paper I referred to, where we looked at the localization capabilities of different arrays, starting from LIGO, 2 LIGO detectors and Virgo, and then adding all the detectors, including one that's called C for China, one that's called A for Australia, and finally we've got the biggest array, and there's lots of data here which you don't need to look at. I want to show just this 0.1 square degree about this error volume I need to identify a galaxy and, at a Z around 0.1 or so. And what I see is that all these arrays have got 0% within this 0.1 degree region, except for when you add detectors in Australia and China. And if you put a detector in Australia and China, you get to 25% of the galaxy of the error ellipses down at that level for 0.1 of a square degree. So that says that you won't be able to do it for all events, but for a certain fraction of events you'll be able to. Not for the more distant events though. As you go further away, and here we've taken a typical source and put it twice as close, and then put it further away at 0.4 gigaparsecs, at 0.8 gigaparsecs, 1.6 and 3.2 gigaparsecs. This array has not got even angular resolution. So you have to ask what fraction of events come within a certain range. And you can see that, and this is another important number, that at 0.8 gigaparsecs, the angular resolution is round about 1 square degree. And in a moment, you'll see why that's important. So now, the next question is, how many events could an array with these extra detectors detect? And the first question we want to know is based on the event rate, based on the observations of binary black holes, how often are they happening in the universe, in the observable universe? And the answer is round about once every 5 minutes. These things are happening a lot. So the equivalent of monitoring all the earthquakes on the Earth, where they're happening about every 15 minutes, monitoring all the space quakes in the universe, and they would be once every 5 minutes, perhaps, with substantial uncertainties, of course. This modeling is all discussed in that paper. I'm not going to go into any of the details, but you have to take into account some models for delay times, and I am rather suspicious about any delay time modeling, how long it takes from the formation to the time they coalesce. But then the question is, how far can we see with this interferometer? And there's two things you can talk about, which is the mean range, and then to talk about the horizon, which is when everything is optimally aligned, how far can you see? And we see that you can get to absolutely crazily large luminosity distances with this 8-kilometer detector. Here is LIGO, advanced LIGO, and here is this 8-kilometer detector. But the numbers look a little bit differently when you look at signal-to-noise ratio. If you look at signal-to-noise ratio, advanced LIGO is this blue curve here. You can see the signal, and we would like to have a signal-to-noise ratio of 8 for any firm detection. So the range of advanced LIGO is around about Z equals 2. The 8 kilometer detector gets you way further, out to about 8. And if you depowered it, because laser power is a significant issue in these detectors, LIGO hasn't got to even to 200 watts yet. So if you depower it down to something comparable to LIGO, it turns out it doesn't change things very much for this type of event. Here is ET, which is like the ultimate detector, and ET sees the whole universe. So here we don't see the whole universe, but it's a pretty substantial fraction. And so we can then ask what the event rates are, and that depends what's most typical of the events we've seen so far. And if they're highly lensed and actually very rare, these numbers might be completely wrong. But if they're not lensed, then these numbers come out about right. And I think the bottom line, so here is redshift, and here is the number of events per year. It's of order 10 to the 4th to 10 to the 5th events per year. We only see the tip of the iceberg at the moment, which is this little bit here, and we would see something between 1 every 2 minutes and 1 every 30 minutes, depending on which is the most typical of the sources. So now let's think about, so we can identify the host galaxies for the nearby sources, but only for nearby sources. Go much further away, it becomes more difficult. Here's a map. I'm not sure how accurate this is, but showing superclusters. And this is a map of superclusters out to 500 megaparsecs radius. So this is a 1 gigaparsec sphere. And the typical size at 500 megaparsecs is about 1 degree, matches quite nicely. So if these were, so the first thing you can think about is that you can start to map the universe in binary black holes. You've got tens of thousands of these things going on every year. So we can find out the density of binary black holes and superimpose it on a visible map of the universe and try to see how they may be located. So you might expect to see binary black holes around here, and few there if they're not in the voids and if they're following the matter. But the most important question is that we'd like to really find out what the total population of binary black holes is, and what is the total population of black holes in the universe. And as George and others have emphasized, this is actually a really difficult problem. This is my sort of naive way of thinking about it. This is a timeline of the universe. There's the Big Bang up at the top left, and sometime after the Big Bang, and we don't know when, if it was population 3 stars, it might be only 500 million years, a binary black hole is formed, maybe sometime later. We are down here at 13.8 billion years, and we can look back a certain distance, but we can only look back a certain distance to our horizon distance, and we can only detect any signals where it satisfies that it's going to occur in this range of time. Any binary black holes that coalesce more slowly are going to be down here, never detectable, and any that coalesce really fast also never be detectable. So and there's such a strong dependence of lifetime of binary black hole on the radius that it seems like it's very difficult for us to make an estimate what the true population is, because we don't know what fraction we're seeing. So it seems to make sense that if you can get statistics on a very large population and see what the event rate is as a function of distance, you may be able to untangle those things. And I guess I should have just emphasized it on this slide. You'd like to find out what the birth time distribution is, what the time to coalescence distribution is, and maybe identify the different populations born in globular clusters being co-evolved from population 3 systems or formed in black holes near galactic nuclei. All of those are possible. So we're not giving a formula for how to do it, but it seems reasonable that with very good statistics you may be able to do that. For neutron stars and multi-messenger astronomy, I think there's also a very interesting message for improved detectors here. We don't know the exact number yet, we're still working on it, but, it looks as if you would expect a detect of order 1,000 binary neutron stars a year. At 800 megaparsecs, depending on the beaming, and other people have emphasized that, you may not be able to see a gamma ray burst, and you may not be able to see an afterglow. The one we saw was at 40 megaparsecs. This is much further away. But the localization ability is better for binary neutron stars because the sources are closer, so a larger fraction can be identified, and galaxy identification, following the same logic I discussed before, may be possible by gravity waves alone. And now the other big problem for neutron stars is that most of the interesting physics of a neutron star coalescence happens in the frequency range 1 to 10 kilohertz. And that's really out of reach of the detectors today. Here are some predictions of the gravitational waveforms for different equations of state from neutron star coalescences. And you can see that that between a kilohertz and 4 kilohertz there's lots of structure. We'd like to see that, but as you saw on those sensitivity curves, the sensitivity degrades there. So that's one of the current detector limitations we have to deal with. The other limitation is, as I've mentioned, this problem of the power, the laser power. It causes a phenomenon called parametric instability that Julie's going to mention, and it also causes thermal distortion of the mirrors. If you were to build an interferometer 40 kilometers long, which is the Cosmic Explorer proposal, the mirrors would have a radius of curvature of 20 kilometers. Thermal distortions in those would have dramatic effects on the shape. So we're scared of trying to build mirrors that long, and that's another reason for staying to a slightly shorter interferometer. There are two approaches that Julie's going to be talking about, the squeezing that's been demonstrated, and another method. I'm just going to introduce this to give you a taster for Julie's talk, which is a method that's called the white light cavity technology, which allows you to pull the sensitivity out up to around 2 kilohertz with a flat sensitivity instead of having these degradations at high frequency. So that's an add-on that you can do for any detector to make you able to look out at those high frequencies and see that interesting physics. So I've just got two slides about the conclusions. First is the sort of science conclusions. the binary black hole events predicted that you should be able to detect between 3,000 and 200,000 events per year. This changes, will change the field totally from, instead of having to deal with every individual event and write a paper about it, we're going to have statistics of huge numbers of systems. The whole field will have to change in how it works. Binary neutron stars, which are coalescing at a rate of about 1 a minute in the universe, thousands will be detectable. We don't quite know how many. I've shown that you can identify the host galaxies of a fraction, only the nearer ones. You can identify the superclusters for more distant events. There was Nakamura-san talked about quasi-normal modes and how important it is to observe the quasi-normal modes. The close sources with detectors that we're proposing will have a signal-to-noise ratio of 200. The quasi-normal mode signals will become quite clear for high mass systems, and so this is an opportunity for unraveling the binary black hole distribution, delay time distributions, and other about the formation mechanisms. But my second conclusion slide is more about the politics, about some things that's going on, just to let you know. The Australian and Chinese Academy of Sciences have proposed a joint meeting which is going to be taking place in Beijing in July this year, and that's about Australia-China collaboration in ground-based gravitational wave detection. Australia's formed a working group under our Ausgrab Director Matthew Bales and Deputy Director David McClelland. And the Gravitational Wave International Committee has got a whole process going on for designing the next detectors, and we are part of that process. And I'd like to invite participation from attendees at the conference to come to this Beijing meeting if you are interested. We'd love to have Singapore and other countries in the ASEAN region to be participating in gravitational wave astronomy, which is the future of astronomy for the next century, I believe. And the last thing I want to mention is that we've got all sorts of opportunities for research collaboration, particularly in experimental gravitational wave detection at the University of Western Australia, and as part of our Ausgrav National Centre for Gravitational Wave Research. So thank you very much. I'll leave you with a couple of pictures.
Right question.
Well, it's also designed to be much cheaper. The ET project is thought to be of the order of $1 billion. This one is, I mean, we don't have a good costing. Really, we have nothing more than guesses. But we know, for example, that the vacuum pipes, which cost maybe $20 or $40 million for LIGO, and similarly for Virgo, will cost about the same for twice the length of the same diameter, because the price of stainless steel has become much cheaper since the time those detectors were built. Many other things would be different. One of the things we would do is to create a facility that's designed not to blow around in the wind, which is what all the other detectors currently do, except the Kagra detector, which is underground. Wind forces are terrible problems on gravity wave detectors, and also temperature stability is critically important. So the sort of cheap solution was to be semi-underground, not completely underground. You don't care what the temperature is for a vacuum pipe, which is going off there, doesn't matter. But this part partially buried to to create good stability.
Right, if that's not the case, let's thank all the speakers for this morning's session.